Hi, welcome to the cycle of my videos about crystal structure refinement, in particular to how to deal with disorder in crystal structures. And I had the idea to record these videos because I remember how much I struggled, and I'm still struggling to learn the practical refinement stuff because there are many different books, many different websites, but you often get, let's say, you get a pack of different tools, but you don't really learn when to use a particular tool, whether you should use one type of hammer or a screwdriver or something else. So hopefully with this type of series, I will show you the ways we can use some refinement tools in practice. Uh, it's something that I really struggled with when I was learning crystallography because you can find, as I say, many different videos, but many of them basically tell you what to click without really saying why are you actually clicking this. So yeah, I hope it will be useful. So I thought it's a good idea to start with some introduction to the disorder refinement, and in particular to define some things so we could have a common language and understand what is happening with the refinement. So at first I would like to refine constraints and restraints and what's the difference between them. So they kind of sound similar, but there is a significant difference. So constraints are like exact mathematical conditions. So basically they're exact, as I said, and the idea is that some variables, and you have many variables during refinement, you can express them in terms of some other variables or some constants, which basically reduces the number of parameters you have to deal with. During the refinement, it's good when you can keep the data to parameter ratio to more than 10 if possible. Of course, if you have some terrible data, it's not possible, but it's good when your crystal structure has data to parameter ratio of more than 10. And sometimes constraints enable you to increase this data to parameter ratio by reducing the number of parameters. Constraints are different to restraints because restraints work as some additional observations. They are not exact, so they are actually refined. And we involve some target values and standard deviations that we want to have. So we're basically defining what's the strength of our restraints that we want to put on our model. And let's go through examples of constraints first. So the first type of constraints I can mention are constraints for special positions. And they are dealt with by the software itself. It will do it automatically. So for example, a constraint is when your atom, whatever, sits on a special position, such as two-fold axis or a mirror plane, and the program automatically defines that occupancy is half, because it's on mirror plane, right? So it's not fully occupied, it's occupied by half, because you have this mirror plane. Another example of constraints are the constraints related to the riding hydrogen atoms. So when we refine hydrogen atoms, we usually place them geometrically, and we say that they ride on other atoms because whenever that other atom changes its position, the hydrogen atoms geometrically still, but they follow the atom they are connected with. So basically, we reduce the number of parameters by relating the positions of hydrogen atoms to the position of the, let's say, carbon atom they are connected with. Another type of constraints are rigid groups. An example of a rigid group is, for example, a six-member ring, which is aromatic. So normally, each carbon atom on a benzene ring, which is connected to something, is a substituent. Each of these carbon atoms marked here in gray has three positional parameters, right? So it has x, y, z coordinates. But if we use a constraint called affix 66, we constrain these six atoms to be a regular hexagon with bond length of 1.39, I think, by default. And We reduce the parameters now because to define this rigid group, we only need 3 atoms. And the parameters related to that rigid group are now 3 rotations of 3 translations of the whole rigid group, not of all the individual atoms. We constrain it to be described by 3 rotations and 3 translations of the whole rigid group. It's pretty useful. Some of other constraints are, for example, fixed parameters, free variables. We'll talk about it a bit later. And also a command you can use exyz and eadp. What does it do? So I was refining a crystal structure of some hydrocarbon which was reduced with alkali metals. The metal that I used for reduction of that hydrocarbon was lithium. But I actually didn't notice that the package of lithium says that there's a high sodium content. And I could really see in the crystal structure that I got that something is wrong. And apparently, the lithium atoms are partially substituted in one crystal by sodium cations. So during refinement, if you use EXYZ constraint, you basically constrain the positions of sodium and lithium to be exactly the same, to model the disorder in a way that the two different ions occupy exactly the same space, they have the same coordinates in your structure, but one of them is, let's say, the structure is more rich in lithium than in sodium. Now let's talk about restraints. So the first restraints I can mention are same, or as I like to say, similar distance restraints. The first one is SADI. Again, same or similar distance. SADI, same distance, right? I like to say similar because just in my mind, if it's similar, it means that it's not exact, so it's not a constraint, it's a restraint, right? But yeah, I think the correct name is same distance. So when we'll be dealing with disorder, let's say that we have some carbon chain. So we have carbon atoms, C1, C2, and C3, but they are disordered over 2 different positions. So you can see that you have another alternative orientation of this group with C2 here and C3 here. And we're going to name them in a different way. And the distances that we can restrain in Shelix are 1-2 distances and 1-3 distances. 1-2 distances are basically between the 2 connected atoms, like literally connected with each other, and 1-3 distances are kind of angle restraints, right? Because if we define distance 1-3 distance, it's basically like defining an angle between the atoms. So what kind of restraints could be right for this particular situation? We can say that, for example, SADI, the standard uncertainty for 1-2 distances is 0.02. That's by default by the program, so you can either write it down in the command or you can just skip it, not write it, just say SADI. So we want C2 and C3 to be similar or the same as C2A, C3A. And we also probably want to write SADI 0.02, C1, C2 to be the same as C1, C2A, C1, C2, C1, C2A. Now it's time for 1-3 distances. For 1-3 distances, the default uncertainty is 2 times larger, it's 0.04 by default. So again, you can either write SADI 0.04 or just skip the 0.04 part. So which 1-3 distances can we make similar here during the disorder refinement? For example, C1, C3, make it similar to C1, C3A, right? C1, C3, C1, C3A. Yeah. A very similar restraint for distances is called same. And SIMU restraints basically generates a set of SADI restraints. The program just interprets SIMU restraints as a set of a lot of SADI restraints. It's very important to have correct positions of the atoms in the input file for Shelix, because otherwise it will mess up everything. So it's very easy to cause accidents if you don't pay attention to the order of atoms. So in general, I usually, when I have, let's say, only one tert-butyl group disordered in my structure, I usually play with SADI restraints. But if I have, let's say, 8 different tert-butyl groups in the structure, some of them are disordered, some of them are not, then I usually go for same, as it's much easier in use, but I'll show you that later. Another type of restraints are diffix or dang. So diffix fixes some distance, let's say 1, 2 distance, to this value, and the default uncertainty standard deviation for or strength of the restraint is 0.02, okay, for 1, 2 distances. Whereas for 1, 3 distances, the default value is 0.04. Instead of writing diffix 0.04 for some 1, 3 distances, 1, 3 distance, you can use dang, because dang by default has uncertainty of 0.04. So it really depends whether you want to have diffix everywhere, or you actually want to be able to distinguish between 1, 2 distances and 1, 3 distances when you read the ins file, to be able to spot the differences easily by, instead of using diffix with a bit larger deviation, to just write down dang. But yeah, we'll talk about it later. And in general, when you deal with some easy disorder, you kind of have two options, right? You can either use same distance restraints to restrain these distances within one fragment to be similar to each other, or you could actually also use diffix and just say that, well, we know that the carbon-carbon bond length when you have sp3 hybridization should be around 1.54, so we can also restrain it all distances to be similar to 1.54 as a default value, right? So in general, it is recommended that if it's some easy case, the refinement can converge okay, giving you meaningful results. It's better to always start with SADI restraints, and then if you notice that something is really wrong, then play with diffix or dang restraints. So in the videos, we'll always try to use SADI or same first, and then we'll go to dang or diffix. Another useful restraint, especially if you have a lot of disordered phenyl rings, is flat. Flat basically makes set of atoms flat in one plane. So let's say that we have a phenyl substituent and it's disordered. The second orientation is, well, somewhere here, right? Our atoms, let's name them C1, C2, C3, C4, C5, C6. That one will be C2A, C3A, C5A, C6A, right? So after inputting some distances on some restraints on appropriate 1, 2, and 1, 2 distances, we can also make sure that they are in one plane, because, well, phenyl substituent should be planar, right? So we can write flat C1, C2, C3, C4, C5, C6, and also for another disorder component, flat C1, C2A, C3A, C4, C5A, C6A. It's very useful. Sometimes if you don't do flat during the refinement, you get some weird appearance of the phenyl ring, but when you use flat, it will help during the refinement. Okay, now the last part, restraints on displacement parameters. So the first restraint I'm going to introduce to you is RIGU. It's a rigid bond restraint, and what it does is it makes the components of the displacement parameters in the direction of the bond equal or similar. As you can see, the strength of this restraint for both 1, 2 and 1, 3 distances is quite large. And that's because it's based on very physically sensible assumption. The fact that in the direction of the bond, the displacement parameters should be more or less similar is a valid physical approximation. So we can use it with quite large strength. And it works based on connectivity table. So if you select some atoms, they will be made similar only if they are connected to each other. So it's different to another restraint that I'm going to introduce to you now, SIMU. SIMU works through space. And what SIMU does is it restrains atom closer than a given distance, by default 1.7 angstrom, to have similar all displacement parameter components, not only these in the direction of the bond, but all of them. And because of that, its strength by default is smaller than for RIGU. And SIMU, as I said, works through space. So let's say if we have tert-butyl disorder, here is our main disorder component, here is our minor disorder component. When we use RIGU, we have two options. Either we can list atoms from first part and then list in another comment atoms from second part, right? Or just list them all together in one line because it works through bonds, through the connectivity table. But if we want to make all of the atoms similar in terms of the SIMU restraint, we want to list all of them together. SIMU works through space. And the last restraint I want to mention, we're not really going to use it in this course, is iso restraint. And what it does, it restrains displacement parameters of an atom or atoms to be approximately isotropic. And because it's not very physically correct assumption, firstly, the strength of the restraint is quite small. It's quite a weak restraint, but we should really use ISOR only in very few instances, and we're probably not going to use it in this course at all. There are only few situations when the use of ISOR is, let's say, allowed. So just a few final thoughts. So whenever we have disorder, we'll be using restraints. It's recommended by the people who wrote the Shellix software and developed it over the years. You can, if you don't want, at some point after finishing dealing with disorder, you can always remove the restraints and see how it works, whether everything's fine, or you can always decrease the strength of the restraints. But in general, it's a good idea to use restraints. It's completely fine to use a lot of restraints, provided that they are reasonable, that they just make chemical sense. For example, you really don't want to restrain a carbon-carbon double bond to be, I don't know, 1.7 angstrom. It's just something chemically not sensible. And if you do restraints like this, it's not going to make your model very good. But if you're using more or less default strengths of restraints, everything should be fine. Also, try to avoid putting extremely strong restraints unless your data is very weak. And final thought, we'll try to keep the data to parameter ratio to more than 10:1. How can we do it? How can we increase the data to parameter ratio? For example, through using constraints, because when we use constraints, we decrease the number of parameters, so the data to parameter ratio increases. Of course, it's not always possible to have such perfect data to parameter ratio if your data is weak, if your data set is not that good, but in general, if possible, we'll try to do that. Okay, now let's have a look at some examples. For now, just let's say on paper, to get familiar with the whole concept of the disorder refinement and what to do. So let's say that we have a tert-butyl group, which is connected to some extra carbon atom, let's say from a phenyl or whatever, right? So let's look at this tert-butyl group from this perspective. So what are we going to see is one carbon atom in the middle and 3 carbon atoms surrounding the middle one. If we refine it anisotropically, we'll probably, if there is some disorder, see that these tert-butyl 3 carbon atoms, their ellipsoids are quite elongated in this plane, which indicates that there might be some disorder. And if we refine it, we would also probably see that between these carbon atoms, especially if you work on isotropic model before making it anisotropic, there are some electron density peaks that are quite high. And these electron density peaks are in fact another orientations of these 3 carbon atoms from tert-butyl groups. So we have one orientation that is right here, and another one which is marked in orange. So what can we do with that? How to refine this disorder? So first, we need to put these different carbon atoms in different parts. The idea of a part is that all atoms that you have in your molecule are in so-called part 0, and they make bonds with each other, right, based on their distance. If we put something into part 1, let's say this marked in black, atoms from part 1 will create bonds to atoms from part 0. And if you put atoms marked in orange in part 2, they will also form bonds to part 0, so to the carbon atom in the middle of the tert-butyl group, but the two parts will not create bonds, they will not be connected with each other. The atoms from part 1 will not be connected to part 2. So we'll nicely be able to look at the structure. So what are we going to do? Let's say that we name these atoms. Let's say this one is carbon 1, carbon 2, carbon 3, and carbon 4. And let's name the other ones similarly. So I usually do it like this. This is the one in the middle is not disordered. That atom will be C2A, that one will be C3A, and that one will be C4A. Okay, now let's see how is it going to look like in the input file for Shellix that we need to prepare in the ins file. So, before adding any extra atoms to the second disorder component, we have atoms C1, C2, C3, and C4. Here are the atomic coordinates. Here are the isotropic displacement parameters. And here is something, these 11s, that relates to something called a free variable. And it's listed here. We'll talk about it in a second. So after we split the atoms into two parts, our ins file would look like that. So we have the first atom that is not involved in disorder, so it's beyond part 1 and part 2, it's in part 0. Then we have atoms in part 1. Then we have atoms in part 2. And I forgot to write it down. Whenever we finish part 2, we should always say part 0 to distinguish between the atoms that we involve in part 2 and all the other atoms that can be beyond these atoms in the ins file. Okay, so as you can see here, we don't have 11s everywhere like previously, right? It's something changed. So I changed the first atom, carbon 1. It remained unchanged, but I changed everything for the other parts. So in part 1 we have number 21, 21, 21. For part 2 we have number -21, -21, -21. What does it mean? These numbers refer to something that we call the free variable. Free variables are listed here. The first free variable is an overall scale factor. It's something that normalizes the observed reflection intensities, and we're not going to touch it. We don't look at this. What is important are other free variables that we're going to add after this number, when we refine disorder. So, what does it mean? 21 means that it's related to the second number in the free variable list. It relates to the second free variable that we're going to input here, and it multiplies it by 1. Okay? What does minus 21 mean? It means that we take 1 and subtract the value of the second free variable. Okay? It's a bit confusing, but let's say our free variable number 2, this one, after refinement, this way, indicated as 0.6. What does it mean? It means that occupancy of the atoms in part 1 will be 60%. They will be in the whole crystal. In 60% of the cases, atoms will adopt this position. They will be in this particular place. And in minus 1 minus 0.6, 0.4. And in 40%, they will be found in these positions. So this number tells us to look at free variable number 2. Occupancy of these atoms will be equal to the second free variable, and occupancy of these atoms in part 2 will be equal to 1 minus free variable 2, in this case 40%. If at some point we had another disorder in the ins file, then we would again have part 1, some atoms, part 2, some atoms, part 0, and then we would relate that disorder to the third free variable. And what we would do for part 1, we would write 31. For part 2, we would write minus 31. So the occupancies that we're going to get will be linked to the third free variable. And that third free variable will be refined separately from the second free variable. Okay? It will get clearer it will get more clear when we get to the actual examples on a computer. If our number here was equal to, for example, 10.5 or 10.333, it means that occupancy of this atom is fixed to half. It's not refined. It's not related to any of these free variables. It's just fixed at 10.5. So occupancy is half, right? Number is 10.5. If, for example, if it lays on special positions such as a mirror plane. If it would be 10.333, it means that occupancy of that atom is also fixed and is 0.333333. Okay, now we know how to create an ins file, more or less, how to deal with order of the atoms, how to introduce these parts and free variables. Now let's talk about restraints. It is recommended that whenever we deal with disorder, we introduce restraints to help the model converge, to not allow it to explode. Using many restraints is not a problem as long as they are reasonable, right? So if we still put restraints with reasonable strength, it shouldn't make our model bad, and it might only help. It's recommended by the authors of the software. Okay, so what are we going to do? We're going to restrain distances first. We're going to restrain 1, 2 distances and 1, 3 distances within this disordered group. How are we going to do that? Let's start with 1, 2 distances. To do that, for now, we will only use SADI restraints. For 1, 2 distances, the default value is 0.02. The strength of the restraints, the uncertainty, is 0.02 by default. Okay, so which distances do we want to make similar? Well, we want atoms from first part, let's say the distance between C1 and C2, to be the same, similar, to the distance between appropriate atoms in the second part, C1, C2A, okay? But because we know that the tert-butyl group has some internal symmetry, right? We also want basically all of these distances to be similar to each other. So what can we write? C1, C2, we want it to be the same as C1, C3, the same as C1, C4, and these will be the same as C1, C2A, C1, C3A, and C1, C4A. Okay? That was for 1, 2 distances. That was easy. Now, for 1, 3 distances, the uncertainty that we put is by default twice as high as for 1, 2 distances. So which distances should be made similar or the same? Well, we want distance between C2A and C3A in part 2, right, to be similar to the distance between C2 and C3 in part 1. So we want to have similar distances in both parts. But again, we know that the tert-butyl group also has some internal symmetry. So we basically want to make all these distances, C3, C4, C4, C2, and these to be similar. So let's write it down. We want the distance C2, C3, similar as C3, C4, and similar as C4, C2. And now from the second part, C2A, C3A, similar to C3A, C4A, similar to C4A, C2A. Great! So now we have restraints on 1, 2, and 1, 3 distances. Now let's do restraints for displacement parameters. So we want to use RIGU restraints first. Their default strength is quite large, 0.004. So we want to put them on atoms from the first part, C1, C2, C3, C4. We just list the atoms that we want to restrain. We also want to do it for atoms from the other part and for the middle atom too that is not disordered. So again, C1, C2A, C3A, C4A. Because RIGU works based on connectivity, not on the distance, like SIMU, we could also just combine them together and just write everything in one line. Okay? And then we can also use SIMU restraint. The default strength is, from what I remember, 0.04, I think. And we just list all the atoms, so the atoms that are disordered and the atom that is connected to the disordered atom, so C1. So again, C1, C2, C3, C4, C2A, C3A, C4A. And that's it. Now, previously I said that there are two types of similar or same distance restraints that we can use, either SADI or same. And I said that same is a bit more difficult to do. I mean, it's not difficult, it's less obvious, let's say it this way. And it's much more easy to make some mistakes. And in general, SADI, as you can see, works quite well. But you can imagine that if you have now, let's say, 10 tert-butyl groups in your crystal structure that you need to make similar, and they're also disordered, it might be a little bit problematic with writing all these restraints and not making any mistake during typing. So As an alternative, I'll also show you that we can use the same thing, so generate the SADI restraints, the program will generate them based on same restraint. How do we do that? So let's say that we again have our tert-butyl group. So I'll just write it down by hand. C1, part 1, C2, C3, C4, part 2, C2A, C3A, C4A, right? And then we finish the line with part 0. We have some coordinates, blah blah blah, blah blah blah, blah blah blah, blah blah blah. Then we have these 21, 21, 21. Here we have minus 21, minus 21, and minus 21. Okay. Now, instead of writing all these SADI commands, we can use same command. And how do we do that? We will insert same command in between here. And how do we do that? We do it like this. So I'll write it down here, what we insert. We write same. Let's say we're using default value, so I don't write anything. So the first thing that we want to do is to relate part 1 and part 2 with each other. We want their respective distances to be both 1, 2 and 1, 3 distances. The program will deal with it on its own, to be made similar between two parts. So how do we do that? We write C2A, C3A, C4A. What does it do? And the order is very important because it makes appropriate distances between these two parts similar to each other, okay? So if I have this order here, C2, C3, C4, I'm writing C2A, C3A, C4A. The same atoms in the same order, just with A's, because they are in part 2. So we're relating part 1 to part 2. But again, we also know that the tert-butyl group has its own internal symmetry, right? C1, C2, C3, and C4. So we want to reflect the fact that if you rotate everything by 120 degrees, it will be the same in terms of distances. It should be the same, okay? So how do we do that? The order here is C2, C3, C4. So now in our mind, we're rotating that. So instead of same C2A, C3A, C4A that was relating two parts to each other, now we're going to relate the same fragment to itself just by introducing this rotation. So what do? We just rotate it in mind and we write, instead of C2, C3, C4, let's say C3, C4, C2, and it's done. We introduce this, we just write these two things and the program will know which 1, 2, and 3 distances should be made similar. So instead of writing down all these SADI, 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 we just do same, done. I think it's pretty useful, especially maybe not super useful if you're using, for example, some structure which has only one tert-butyl group, because then you can easily deal with it just by inputting few SADI restraints. But as I said before, if you end up having few different tert-butyl groups, part of them are disordered, you want to make them all similar, both between components and between all the groups that you have in your structure, the same command is very powerful. So now another example, just to show you again how to write distance restraints in action. So let's say we have THF molecule, right? So let's say it's O1, O2, O3, I'm stupid, sorry. C1, C2, C3, C4. And let's say that our THF is disordered and all of the atoms are disordered. So the new names would be O1A, C1A, C2A, C3A, and C4A. Okay, let's try to write down all the SADI restraints, and then again, let's try to do the same thing by using same. Okay, let's play with the SADI. Which distances do we want to make similar? Well, we want distances from part 1 to be similar to distances from part 2, right? So O1 C1 should be the same as O1A C1A. But again, we know that the molecule itself has some symmetry, right? So we also want to make these distances all similar to each other. So let's write it down. Let's write 1, 2 distances first. So O1 C1, O1 C4. We made these two similar. And we want them to be similar to O1A, C1A, and O1A, C4A, right? So we took care of the 1, 2 distances to oxygen. Another set of distances, SADI 0.02. Now let's take care of, I'll use a different color maybe, that will be easier to visualize it. Now let's make these similar. Again, both between different parts and within the same part because of the internal symmetry of this fragment. So C1, C2, similar to C3, C4, similar to C1A, C2A, similar to C3A, C4A. Done. Another one, the last one is 1, 2 restraints. C2, C3, the same as C2A, C3A. C2, C3, the same as C2A, C3A. It looks super boring, and it is, but if you work with graphical interface such as OLEX, you can just click on appropriate distances or also use some OLEX tricks, but I usually do it, let's say, semi-manually. So if you just click on appropriate bonds and click and input SADI on your screen, you'll just introduce the command, so it will be much easier. Okay, now let's take care of the 1, 3 distances. So what kind of distances are we dealing with? For example, that distance between C1 and C4 and C1A, C4A, right? Let's write it down. SADI 0.04 because uncertainty is larger, because it's 1, 3 distance. C1, C4, C1A, C4A, right? Now let's take care of the distances that involve oxygen atoms. So we want to have these two, and again, we want to make distances from both parts to be similar to each other, and we also know that the molecule has its own internal symmetry, so these two distances should be also made similar. Okay, O1 C2, O1 C3, O1A, C2A, O1A, C3A. I think one more, SADI 0.04. Which distances do we still have to take care of? Distances from C1. So distances from C1, we already took care of the C1, C4 distances here, but we still have to do C1, C3, which is the same as C4, C2, and similarly in the other parts. So let's do it. C1, C3, similar to C2, C4. It's similar to C1A, C3A, similar to C2A, C4A. And I think that's all in terms of 1-3 distances. Yeah, we have three different SADI three different sets of restraints for 1-2 distances, and three different ones for 1-3 distances. So that's again with SADI only. Now let's do similar thing with SAME. So let's say I'll just write down all of the atoms as if they were in the input file. O1, C1, C2, C3, C4. Part 2. O1A. I'm just checking if I didn't make any mistake, but I didn't. O1A, C1A, I'll write it down again. C1A, C2A, C3A, C4A, and part 0 to finish the line. Okay, so again we have some coordinates, blah 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 blah. Here our numbers, there's F-var somewhere, right? So the first number, we don't care about it, and then the second number, let's say we input 0.6, so it will start the refinement with 0.6 occupancy to give it just some starting point, and here will be to 1, to 1, to 1, to 1, to 1, and here, of course, minus to 1, minus to 1, minus to 1, minus to 1, and minus to 1. Okay, and now I said that if we want to use same restraint, we have to input the two same commands in this place. So how are we going to do that? So as I said before, first we want to relate two different parts to each other. So if our first part was O1, C1, C2, C3, C4, then we should relate it to O1A, C1A, C2A, C3A, C4A. And now the slightly more difficult part, we want to restrain distances within the same part to reflect the internal symmetry of the molecule, right? So let me just write down our THF. O1, C1, C2, C3, C4. And we know that we have some symmetry here, right? So what are we going to write down here would be C1 by symmetry is related to C4, right? So we write O1 stays the same because it's related to itself, but C1 is related by symmetry, by internal symmetry to C4. So I write C4. C2 is related by internal symmetry to C3. So I write C3. C3 is related by internal symmetry to C2. So I write C2, and C4 is related by its internal symmetry to C1, so I write C1. So, and again, as you can see, instead of writing all these SADI restraints, we managed to model exactly the same thing using just two same lines. Two lines saying same command. They're not the same, right? Okay, I hope it was helpful, and thank you very much for watching the video.